Consideration of global warming 7. The impact of nuclear tests on temperature. ATCAS 6919. Introduction. Looking at Figure 1, it is suggested that nuclear tests may have an impact on temperature. Therefore, I will attempt to verify this using mathematics. However, since I do not have detailed data, this will be an estimate. The meteorological data in Figure 1 is based on the data for Tokyo from Reference 1. The annual primary energy supply is based on References 3 and 4. The frequency of nuclear tests is based on Reference 2. The period from 1961 to 2025 was chosen because, according to Reference 1, hourly observation data for each day is only available for this period. Also, to standardize the solar position, the summer solstice was chosen. Similar trends are observed for the vernal equinox, autumnal equinox, and winter solstice, but the impact is less than that of the summer solstice. It is presumed that many nuclear tests were conducted near the summer solstice in the northern hemisphere, so the summer solstice was selected as the focus. Finally, by closely observing Figure 1, it can be seen that the nuclear power plant accidents, shown in red in the nuclear test frequency column, are followed by high temperatures, the year after the 3 Mile Island accident, 4 years after the Chernobyl accident, and the same year as the Fukushima accident. The degree of temperature increase is proportional to the scale of the accident. There appears to be a correlation. Methods. Table 1. According to Reference 1, the temperatures at the summer solstice from 1961 to 2025 are shown in Table 1. The average values used here are the usual arithmetic means. Only excerpts are shown due to space constraints. Table 2. Furthermore, according to Reference 3, the trend of primary energy supply is shown in Table 2, excerpt. Table 3. Finally, according to Reference 2, the number of nuclear tests since 1961 is shown in Table 3, excerpt. Number of atmospheric and underground incidents omitted. Figure 2. From Tables 1 to 3, Figures 2 to 4 are obtained. For Figure 3, since there is no data after 2022, the value for 2022 is used. For Figure 4, the frequency is the total number of nuclear tests. In the approximation formula, the use of 16 decimal places is the same as CGW7. Figure 3. Figure 4. Methods, continued. The temperature trend in Figure 2 is approximated by a sixth-degree polynomial, denoted as F1 is x. The primary energy supply in Figure 3 is similarly approximated as F2, x, and the nuclear test frequency in Figure 4 as F3, x. The coefficients alpha and beta that satisfy the equation F1 x equals alpha F2 x plus beta F3 x were determined. Microsoft's M365 Copilot was used for the calculations. Results. F1 x equals 7.169 0.1134x plus 0.001355x superscript 2 F2 0.9143x plus 6.0748 plus 0.06985 0.0034x 0.000048 superscript 2 F3 0.8042x 0.9076. When graphed, this is shown in Figure 5. Figure 5. The x-axis represents the year, with x equals 1 corresponding to 1961. The y-axis represents temperature, degree C. With our superscript 2 equals 1 and our MSE equals 0.0061, the fit is almost perfect. Next, Figure 6 shows how F2, x, and F3, x, contribute. Figure 6. Here, y1 equals alpha F2, x, y2 equals beta F3, x, with the x-axis as before, and the y-axis representing the contribution to temperature, degree C. Discussion. First, the coefficient of determination, our superscript 2, for the sixth-degree polynomial approximation of F1 x, shown in Figure 2 is extremely low at 0.194. However, meteorology is complex, and increasing precision with other approximation methods may lead to overfitting and losing sight of the essence. The coefficients of determination for F2, x, and F3, x, are acceptable. It is well understood that F1 x is not determined solely by F2, x, and F3, x, but the purpose of this study is to mathematically prove what was intuitively felt from Figure 1, so the focus was narrowed. Discussion continued. Next, looking at the behavior of y2, it contributed to warming for x equals 0 of 15, but after x equals 15, it contributed to cooling. This can be inferred to be due to the type of nuclear test, i.e., whether it was atmospheric or underground. There were reports that after nuclear tests in the Democratic People's Republic of Korea, severe cold damage occurred, leading to food shortages, which supports this. Furthermore, if we assume that no nuclear tests were conducted, the behavior would follow y1 in Figure 6, and the heat generated by energy consumption would have promoted warming. However, in reality, the temperature has only risen by 1 to 2 degrees Celsius, suggesting that there must be a mechanism in nature that maintains balance. The future described in reference 5 feels increasingly realistic. This is shown in Figure 7. Finally, some people on social media show graphs like Figure 2 and claim that there is no global warming, but this study proves that such claims are incorrect. Figure 7. Here, x equals 1 corresponds to 1875 on the x-axis, and the y-axis is the annual root mean square temperature, degree C. The highest our superscript 2 value is for the red curve, which is a two-term sine wave approximation. Conclusion. Among the effects of nuclear tests conducted from 1945 to 2017 on the weather, the impact on temperature was mathematically demonstrated. References. Reference 1, Japan Meteorological Agency, Past Weather Data Search, Tokyo, URL omitted. Reference 2, Japan Jinsukyo, Known Nuclear Tests Worldwide 1945 to 1998, Robert S. Norris, William M. Arkin, Natural Resources Defense Council, Bulletin of the Atomic Scientists, NOV/DEC 1998, URL omitted. References, continued. Reference 3, Agency for Natural Resources and Energy, Comprehensive Energy Statistics 1990 to 2022, Trends in Domestic Primary Energy Supply 1965 to 1989, Comprehensive Energy Statistics 1953 to 1964, URL omitted. Reference 4, Agency for Natural Resources and Energy, Annual Report on Energy, Energy White Paper 2018, URL omitted. Reference 5, Author's own work, Consideration of Global Warming 6, URL omitted. The end.